Okay, welcome everyone. Today, we're unpacking a massive physics breakthrough that honestly feels like it was pulled straight out of science fiction. We're going to explore the mind-bending concept of time flipping in quantum physics. We're looking at a fascinating new paper introducing something called indefinite time-directed quantum metrology. Now, if that sounds incredibly complex, don't worry. We're going to break it all down step by step in this explainer. But to ground ourselves in reality before we get deep into the quantum weeds, we really have to ask, why does this actually matter? Well, detecting the most elusive phenomena in our universe, things like the ripples of gravitational waves or the ghostly presence of dark matter, relies entirely on pushing the ultimate limits of measurement precision. I mean, these signals are incredibly faint. They're so easily drowned out by the chaotic cosmic noise of the universe itself. We're essentially trying to measure the unmeasurable. And to do that, physicists need tools that operate at the absolute edge of what the laws of physics even allow. Okay, let's dive into this. To guide us through the advanced quantum mechanics we're about to unpack, here's our roadmap. First, we'll look at the quantum measurement bottleneck. Second, enter the time flip. Third, precision without entanglement. And finally, surviving a noisy world. Let's start right in with part one, the quantum measurement bottleneck. Before we go any further, let's quickly define our core topic. Quantum metrology is the science of making extremely accurate estimates of a system's properties. So this isn't just about reading a thermometer, right? This is the science behind the world's most precise atomic clocks, highly sensitive magnetometry, and, as we just mentioned, dark matter searches. These tools are quite literally the ultimate yardsticks of our universe. But there are speed limits to this precision. For a really long time, we've dealt with two main limits. First is the standard quantum limit, or SQL. If you use regular, uncorrelated particles to measure something, your precision scales linearly. It's good, but it's not great. Then you have the absolute holy grail, the Heisenberg limit, or HL. This offers super precision, scaling quadratically instead of linearly. But here's the catch. To reach it, scientists have traditionally been forced to rely on quantum entanglement. An entanglement is notoriously delicate. A single stray photon or even a tiny fluctuation in temperature can cause those entangled states to just collapse instantly. And when they collapse, boom, you lose your precision. That fragility is a massive bottleneck. Which brings us to part two. Enter the time flip, a really exciting solution to this exact bottleneck. Now, what's really interesting about this slide is how this new approach is actually mapped out in the Indefinite Time-Directed Metrology, or ITDM scheme. At the top, we have a control qubit, and right below it, a series of pure product probe states. Now, those are basically our standard unentangled baseline particles. But instead of a standard encoding operation, the target parameter is encoded using a time-flipped gate. It is a completely new framework for how a quantum state processes information. So let's look at how this process actually unfolds. Step one is pretty straightforward. You prepare your control qubit and your pure product probe states. And remember, importantly, these are completely unentangled. Step two is really where the magic happens, applying the time flip supermap. This creates an indefinite time direction. It means the quantum process actually lacks a fixed temporal arrow. It literally exists in a coherent superposition of moving forward and backward in time simultaneously. Crazy, right? And finally, step three is decoding that state via measurement to extract your highly precise parameter data. Moving to part three, precision without entanglement. This is really the aha moment of the whole paper. The authors state this beautifully in the research. Now, before reading this, note that QFI stands for quantum Fisher information. That's essentially the mathematical limit of how precise a measurement can possibly be. They write, entangled probe states produce a higher QFI than optimal product probes without enhancing scaling, highlighting the non-essentiality of entanglement. Let that sink in for a second. For decades, we just assumed delicate entanglement was this strict toll you had to pay to achieve Heisenberg-level precision scaling, but this protocol mathematically proves that entanglement is actually non-essential to beat the standard quantum limit. And this brilliantly illustrates that exact finding. What we're looking at here are map plots of that quantum Fisher information. The bright yellow spots represent the peak precision capabilities. On the left sphere, we're looking at the precision limits using optimal, completely unentangled product states. Now scan over to the right sphere, we see the exact same metric using all possible entangled states. Just look at those peak values. the symmetric product probe states on the left can reach the exact same maximal Heisenberg scaling as the highly complex, superfragile, entangled states on the right. Okay, part 4, surviving a noisy world. Let's see how this highly theoretical math actually helps engineers out in the real world. Because real quantum environments are incredibly chaotic. They're just filled with depolarizing noise, which is basically the chaotic environmental interference that normally scrambles and destroys those delicate quantum states. So let's impartially compare 3 strategies to see how they hold up. The regular strategy uses standard unitary encoding, and its fragility to this noise is extremely high. The switched strategy uses a concept called indefinite causal order, meaning a superposition of the order of operations, and that offers moderate fragility. But our flipped IDDM strategy, using indefinite time direction, has remarkably low fragility by comparison. And the data backs this up perfectly. Look at this Fisher information comparison across a noise parameter, which is denoted as Q on that horizontal axis. Notice how the time flip method, that's the blue line, consistently and drastically outperforms both the regular method, shown in orange, and the switch strategy, shown in green. Even when non-optimal probe states are used, the time flip method just proves its supremacy in maintaining high precision information against all that disruptive noise. Even better, this advantage scales up remarkably well. This chart compares multi-party Fisher information against the number of qubits. Check out the massive oscillating peak of that blue line, representing the flipped strategy. Even as you scale up to multi-qubit systems, the time flip method reaches drastically higher precision peaks than the standard additive regular method. It just visually hammers home exactly how much more metrological power you can squeeze out of the exact same number of qubits just by using time superposition. We're talking exponential precision gains here, without the fragile engineering headaches of the past. So what should we all take away from this? It's a literal paradigm shift for quantum technologies. Number 1, this method reaches Heisenberg limit precision. Number 2, it completely eliminates the strict need for fragile entanglement, which removes a huge engineering bottleneck. Number 3, it achieves this by harnessing the mind-bending physics of existing in a superposition of forward and backward time. And crucially, number 4, it outperforms standard methods in the chaotic, noisy environments of the real world. Which leaves us with this final, provocative thought. We are learning to manipulate the very flow of time at the quantum level, basically just to build a better ruler. So if time flipping can rewrite the fundamental rules of measurement, what other quantum barriers are about to fall? Thank you so much for joining me on this explainer. I hope this sparked your curiosity to keep exploring the quantum frontier.